Okay, hi everyone. This is just a short video on a series. It's only a short chapter, this chapter, but it is an important one actually. And it's quite nice. It's quite good fun. I expect you'll probably like most of these kinds of questions, but they can make them a little bit tricky. But the the 90% of questions which you see, which have a sigma in for this standard anyway, are pretty straightforward. But it's an important mathematical symbol, so I'd like to waffle on to you about it if I may. Okay, so. Um, Now, some of this you'll probably be aware of already. If we're going from 1 to n, and we've got a function of r in here, yeah, we use r to denote the variable within here, but this could go up to say n could be a number here, n could be 100 or something like that. But if we just write n, then we're going up to the number n. So what this really means is I'm going to plug 1 into my function first. And then I'm going to plug 2 into my function. I'm going to add it to to the value of whatever 1 was after I popped it in the function. Then I'm going to plug 3 in, etc., etc., all the way up to f of n minus 1 and then f of n. That's what the actual meaning is behind that statement. So let's take a few examples. We've got, let's say, 2r squared minus 1 from 1 up to 7. That simply means 2 times 1 squared minus 1 plus, and let's put this in brackets so it's clear, plus 2 times 2 squared minus 1. Now, I won't write them down, all of them, because obviously it will get very boring, but all the way up to 2 times 7 squared minus 1, and that would complete the sequence. So that's what sigma actually does. Now, there's lots of interesting things you can do actually, and I hope from this example actually that I can show you that this will be true. Firstly, if you've ever got, and this is where the sigma sign, you'll notice, works exactly like the integral sign, yeah? If you've ever got from 1 to n, so whatever number you like really, of k times f of r, what you're allowed to do is take the k outside of the sigma, yeah, and just multiply it by k at the end. That is really just factorizing. That's all I'm really doing there. Because, and I'll show you this in a second with this result up here, yeah? Okay, right. What I'm also allowed to do, and you'll note that you're allowed to do that last trick which I showed you, that's exactly the same as it works with the integral. You're allowed to pull constants outside of the integral. Okay, so what else can we do? Well, we can do this kind of crazy trick. If you've ever got two functions added together, which happens all the time, um, you can break it up. So you do the sum of the first function from 1 to n plus the sum of the second function from 1 to n. Now, how can I use these two results for that last situation up here? I could use it like this. I don't have to work it out like that. I could actually break it up because if I'm dealing with the sum of 2r squared minus 1 from 1 to 7, I could in fact make that the sum of 2r squared from 1 to 7. This does work with a minus, obviously, yeah. Minus the sum from 1 to 7 of 1, yeah. Now, I could then pull out that 2, making it 2 times the sum from 1 to 7 of r squared, minus just the sum from 1 to 7, just using 1. And that's what I can do. So I can break up these sigmas just like I do with integration. That's an important trick which we're going to use throughout the exercise, really. So make sure you've got the hang of that. It's worth pointing out as well that really for the first exercise, you're going to learn two standard results. But then you're going to turn two more in the second exercise, and I might just teach them all in one go. The standard results are as follows. If you're ever summing from 1 to n a constant, like 1, for example, like we had up above, well, what this really means, you're going to plug 1 into a function. Oh, but hang on, the r isn't there. The k is a constant. The variable r, which we normally use in sigmas, isn't there. So what this really means is k plus k plus k n times. Yeah, there's going to be n k's there. Because when we plug 1 into a constant, we don't plug it into a constant. It isn't there. So it's just really counting how many times we're adding the constant. So I'm sure you'll agree that that is simply kn. Yeah, that's the first standard result. If you have a summing from 1 to n, a constant k, it simply equals kn. The second standard result is what I would describe as the sum of the natural numbers. If you're ever summing the natural numbers from 1 all the way up to n, well, as you can see, we're plugging 1 into R, we get 1. We're plugging then 2 into R, we get 2. Plugging 3 into R, we get 3. And that will go all the way up to n. Now, there's lots of ways you could sum the natural numbers. One way of looking at it is this simply you generates the triangle numbers 1, 3, 6, 10, etc., etc. And you might be aware that the formula for that is n times n plus 1 over 2. Another way of looking at it is this is simply an arithmetic sequence with first term 1 and common difference 1. And so what we could do is say the sum of n terms is n over 2, 2a plus n minus 1 times by d. And that simplifies to n over 2, 2 plus n minus 1. Well, that's going to be just n plus 1. And so we get this standard result, n times n plus 1 over 2. There's loads of ways of proving that, though, that the sum of the natural numbers adds up to n times n plus 1 over 2. I might do it with my rectangles, actually. Should I do it with my rectangles? Yeah, here's a little graphical proof for why the sum of the natural numbers should be n times n plus 1 over 2. There's lots of ways of proving this. I could say, well, okay, there's my first natural number. That's n is 1. Yeah, when I'm doing n is 2, I could draw it out like this. Let me see. N times n plus 1. Oh, yeah. In fact, yeah, let me use my colours. Yeah, I'm going to need colour here. So bear with me on this one. What do we get? 2 times 3 is 6. Divided by 2 is 3. So, yeah. Oh, I should have used a different colour there. Sorry, I'm struggling here. I don't know why I'm giving you three different proofs here for the same result, but I just kind of like to do it sometimes. um, oh, I might even just leave this proof. Maybe I'll do it at the end of the video. But there's a lovely way you can look at it, like with rectangles, basically. And in fact, I might have even shown this to you as a class. I'm not sure, but the proof where really you're just dealing with half a rectangle. Mm. You can look at a triangle. Yeah, maybe I will quickly show you it. 1 second. Sorry, you know how indecisive I am. We can look at triangles. You know the triangle numbers. We can look at them as half rectangles, really. Um, yeah, there we go. Um, I'm just gonna do this. Just humour me for a moment and go with me on this. Uh, 3, 4, 1, 2, 3, 1, 2, 1. So what I'm going to do here is I'm going to show you that formula is n times n plus 1 over 2. If we have this as n equals 1, yeah, n equals 2, n equals 3, n equals 4. What I'm showing you basically is how to add up the natural numbers, like, and this is like 4 plus 3 plus 2 plus 1. Well, what could be the formula for this? Well, what we could do is turn these all into rectangles by adding a dot there, adding 3 dots here, adding 6 dots there. I've done that kind of wonky, haven't I? That's better. Adding 6 dots there, adding 10 dots here. Um, Here we go. Okay, and what do we notice? Well, we notice there's half as many reds as there are blacks, precisely half. And so all I've got to do to work out the number of red dots each time is n times n plus 1. And that's because this is 2 by 3, yeah? And that's 3 by 4. You see what I mean? It's a funny little visual proof of like the fact that the result is n times n plus 1 over 2. And there we go. Anyway, sorry, I got completely distracted there. You know what I'm like. I do sometimes get distracted by just some fun maths, which I'd like to do. Let's get back to the topic in hand. So we've got our two standard results. Now, the whole exercise is about just using those two standard results, even though actually for this whole exercise, because you're each time dealing with arithmetic sequences, you could actually use the arithmetic sequence formula for loads of these questions. But let's just have some examples now. Of using this. Yeah, so we've got sum of, I don't know, 1 to 25 of 3r plus 2. Now, what you could do if you'd never done this chapter before is write down the first few terms, realize it's arithmetic, and then use the sum of an arithmetic sequence formula. I'm not going to do it like that because I want to show you we could in fact do it like this. We can rewrite this as, well, let's do it step by step, even though I'd normally jump this step and go straight to the second line of working. This is the same as the sum from 1 to 25 of 3r plus the sum from 1 to 25 of 2, which is the same as 3 times the sum from 1 to 25 of r plus the sum from 1 to 25 of 2. And now I can just use my two standard results. Normally I would have gone straight down to that second line here because it's just obvious, yeah? And all I'm using here, just to recap, all I'm using is those two principles. Sum of k times f of r is k times sum of fr, and if you've ever got two things added together in a sigma, two functions, you can do them separately as two separate sigmas. I'm just using those two principles, and now I'm going to use the standard results, yeah? Because what have I got here? I've got this, which is 3 times by, okay, n is 25, so 25 times 26 over 2. And here, well, n is 25, so 2 times 25. I can now just work that out on my calculator, and I'm sure you'll agree it was quicker than using the sum of an arithmetic sequence formula. So 25 times 26 divided by 2 times 3 plus 50. Okay, I'm getting 1,025, yeah? I'm quite happy to show you very quickly that the sum of an arithmetic sequence formula would have given me the same result. If you think about the first few terms, it would have been 5 plus, and then when you plug in 2, 8 plus, going on all the way up to whatever the last term is by looking at is 77. But what have we got here? We've got A is 5, we've got D is 3, we've got N is 25, and so the sum is 25 over 2, 10 plus 24 times 3. And sure enough, what do we get? 24 times 3 is 72. 82, we get 41 times 25. And 41 times 25 is 1,025 as well. See, you can do it actually in two different ways, but I strongly suggest that you start doing it this new way, which we're learning in this chapter. Okay, so that's a bog standard simple question. A few comments I might make. Look out for this situation. Sometimes you get a question like this, find the sum of from 11 to 99 or something like that, 3r plus 1. Yeah, if you're doing that and it starts at 11, you've got two choices. You could treat it as an arithmetic sequence, just work out the first term and do it like I did over here. Or you can write, okay, well, that's the same as from 1 to 99, 3r plus 1. And then minus, now people often get this wrong, but you really should go from 1 to 10, not to 11. Most people write 11 there, but it's up to 10, 3r plus 1. The reason why we don't write 11 there is because we need the 11 term in the sequence. The 3 times 11 plus 1, that is part of our sequence, so we don't want to take it away. And then we can use the fact that that's the same as 3 times r from 1 to 99 plus sum from 1 to 99 of 1, that would just be 99, yeah, minus 3 times the sum from 1 to 10 of 3r plus 1 minus, well, let's just put minus 99, well, plus 99, sorry. Yeah, and that's 1 to, oh, no, plus 10. I apologize, I'm getting it wrong. That's what happens when you rush. You get it wrong. Don't rush. I'm talking to myself there, not you. Plus the sum from 1 to 10 of 1. Yeah, so you'll be adding 10. Okay, and then you can work it out. It's not particularly interesting what the final answer is. I want to get onto some of the tougher questions, and I also want to get onto the sum of the squares and cubes. You'll be doing this tomorrow, so I might as well just talk about it now. Now, the sum of the squares and the sum of the cubes, and I don't think you get this in the formula book. I'll check that though, because I might be wrong there. The sum of r squared from 1 to n is n over 6 m plus 1 do m plus 1. Something interesting I want to point out in a second, but I'll just show you the sum of the cubes first. The sum from 1 to n of the cubes. So what we're doing here is we're summing the square numbers there, and we're summing the cube numbers here. This is easy to remember for a very important reason. Yeah, there's some really interesting things going on here. Right, firstly, note, when you sum a linear sequence, if we go back to the standard results up here, so I might label these standard results as well. When you're summing a constant, you get a linear sequence. When you're summing a linear sequence, you get a quadratic. When you sum a quadratic, sum the squares, you get a cubic. When you sum the cubes, you get a quartic. And guess what? That pattern will continue. Yeah. Now, another thing worth pointing out is this is the square of the sum of r. Recall that the sum of r was n plus 1 over 2. Yeah. Well, that squared gives me this result. That means something really, 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 really interesting. Look at this. 1 cubed plus 2 cubed plus 3 cubed plus dot 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 is exactly the same as 1 plus 2 plus 3 dot 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 squared. Wow, mind blown. Weirdness, yeah. That's a really interesting fact. It really is. It always tickles me to see that that is true. Now we're going to prove those results by induction. The easiest, they're really simply proved by induction. But you haven't done inductive proofs yet, so you've got that to look forward to. Definitely induction is the most sensible way, I think, in some ways to prove those results. Although I have seen other proofs of them, I think the inductive approach is quite sensible. Okay, now using this is no different to using, other kinds of the way we were dealing with the standard results from the first two things we did. Yeah, so these are more standard results. You can use them without proof unless you're asked to prove them in an induction question or something like that, but it's perfectly acceptable to use them without proof. Now, I'll just show you a couple of kinds of questions that you might get asked. You might get asked something like this. Prove that the sum, and I'm just going to pick one at random from the mixed exercise. Let's do this one. Okay, the sum from 1 to n of r times 2r squared plus 1 equals a half n plus 1 n squared plus n plus 1. Yeah, now this is going to be pretty tricky. Yeah, what we're going to have to do, well, it's not going to be pretty tricky, it's just going to be long algebraically, and you'll probably really quite enjoy it. What we're going to do is we're going to break this up. First thing I'm going to do is left-hand side is the sum of, and I'm going to multiply out those brackets, 2r cubed plus r from 1 to n. And that equals 2 times the sum from 1 to n of r cubed plus the sum from 1 to n of r. Now I'm in a position where I can use my standard results. That's going to be 2. Now the sum of r cubed, I said it was n squared, n plus 1 squared over 4. So there's going to be some cancelling there. And the sum of r is n plus 1 over 2. Now at this stage, do not multiply out the brackets. Factorize, yeah? This is also over 2, so I can take out a half. But, that's the same as that, yeah? So I can take out the half, but I can also take out an n and an n plus 1, because that term has an n and an n plus 1, and that term has an n and an n plus 1. Now, what will we need to multiply that by? Well, n, because n times n would give me the n squared. and then n plus 1, and then plus 1 on the end, because that times that gives me that. And then if I multiply that out, I get a half n plus 1, and when I say multiply out, I mean this bit here in the brackets, and then I'm going to get n squared plus n plus 1 as required. Yeah, that's the kind of thing you might do in the second exercise. There are trickier questions than that, and certainly the challenge question I'd love to show you because it's really quite interesting, the challenge question. I'd like to talk about sums of sums and sums of sums of sums, but that's where it gets really, really interesting. Let me show you a couple more questions from exercise 3A, because there are a couple of nasty questions in there. I want to show you question 6, because I reckon you'll ask me about question 6. Question 6 says, show that, apologies for that sound, that just means people are emailing me, the sum from 1 to n squared, ooh, we're going up to n squared this time, of r, minus the sum from 1 to n of r equals a half n cubed minus 1. This is just part A, and then we can do part B. Okay, similar approach, left-hand side equals, okay, this time I can use my standard result straight away, but n is going to be replaced with n squared, yeah? So rather than having n plus 1 over 2, I'm going to have n squared plus 1 over 2, minus, and then this is simply n plus 1 over 2. Now, like I say, resist the temptation to factorize out for as long as possible. We can take an n over 2 out of each one, because but we can't take an n plus 1 out this time, sadly. So I'm going to do n over 2 times by n squared plus 1, minus n plus 1. Keep it in brackets, watch out for sign errors. And then if you multiply that out and simplify, you're going to get plus n and minus n, and then you're going to have minus 1 on the end. So you are, in fact, going to get exactly what they've got written down above, a half n cubed. The n cubed comes from these two terms. Then we're going to get a plus n, take away an n, that disappears, and a minus 1 as required. Yeah, so that's how that question works. How does that help us in part B? Well, it helps us in part B because in part B it says evaluate the sum from 10 to 81 of R. Okay, right, so we're going to need a little bit of thinking here. We need to relate it to the first part of the question. Well, firstly, like I say, when you're dealing with anything where it doesn't start with 1, you always have this option. It's not always the best option, but it's an option. Yeah, it's like you can always rewrite it as a sum from 1 to 81 of R minus the sum from 1 to 9 of R. Now, why is that in a really similar format to this first bit? Well, have a close look and realize that n is in fact 9. If you had n is 9 in there, you'd have exactly that result. So what we can now do is just let n equal 9, because we know this equals 9 over 2 times by 9 cubed minus 1. And so that's 9 over 2 times by, what is that, 728? And I'm now going to use my calculator. 728 times 9 divided by 2. 3276. Hopefully that's the same as the answer in the back of the book. Okay, or one of us is wrong. Let me just do one more question for you. I just want to go through question 13 because I seem to recall that confused students when they asked me about it relatively recently, a year ago or something. Okay, we've got, given that the sum from 1 to n of f of r equals n squared plus 4m, find f of r. Now, I'd argue you need to know something else a little bit more about this, yeah? Do you recall me saying that if this is linear, this will be quadratic. If this is quadratic, this will be cubic. If this is cubic, this will be quartic. I need that result. I almost wish in this question they said, given that f of r is of the form AR plus B or something like that. So I'm going to do that first. Let f of r equal AR plus B. I think to do this quickly and easily, you do need to know that that is a linear function, because then we can write the left-hand side as sum from 1 to n of AR plus B equals n squared plus 4m. And we can use our little tricks with the sigma to write that as A times the sum from 1 to n of R plus the sum from 1 to n of B. That is, oh, and I should say that's identical to n squared plus 4m. Right, now I can use my standard results. Standard results, A times n plus 1 over 2. A times, oh, go on and I'll write it like this. N plus 1 over 2. Really no need for that many brackets. Plus Bn. That is identical to n squared plus 4m. And then I can use the method of equating coefficients. When I multiply that out, I'm going to get an squared over 2 plus an over 2 plus bn is identical with n squared plus 4m. Well, have a look at this. The coefficient of n squared is 1. And that is only true, that can only be true if a equals 2. Then you're going to get 2 over 2 and you're going to get n squared on the left hand side. And if a is 2, you've got an n there plus a bn equals 4n, and so b must be 3. And you've done it. F of r is 2r plus 3. Hope that makes sense. I'm going to finish off the video here because it's gone on a bit long now. But yeah, I hope that gives you a little few pointers on exercise 3A and 3B. Definitely the challenge questions. I want to stick up a little bit of work about that, but they're great fun. Brilliant. Okay, best of luck with the work and yeah, keep up the hard work. Bye-bye.